Again, B Part 6, Exterior Algebra. Lecture 3, Numerical Example. Given the function f(xi) is x squared plus y cubed, and the vector field x, t, partial of x, partial y, times 4, compute df applied acting on x, and show that it is equal to x of f. This I call relation 1, which I want to derive this equality here. Now, step 1, let's put it here. Compute the differential df, which is one form. Attention, f is 0 form, df is one form. So df is partial f with respect to x dx plus partial f with respect to y dy. Recall that dx and dy are the basis of the cotangent space, you see, the dual space. So I just take the derivative of f is given. You see this will be 2x, derivative with respect to x, and derivative with respect to y, partial derivative is 3y squared, which over there, dy. So this is df. Attention now, df is one form. You see, this here, these are the one form basis. You see, dx and dy. So the step 2, compute df acting on x. You see? So I already have df and I have x, which is given 3 partial respect to x plus 4 partial respect to y. You see, that's a vector field here. Let's apply df to the vector field x. We have both. So the action of one form on a vector field x is linear. See, I just applied this. It's quite easy because this is 3 df applied to partial dx, 4 df applied partial y. But the left hand side of 1, you see that's the left hand side of 1, you see we can write clearly that is df partial of x is 2x dx plus 3y squared dy applied to the x, the delta, the scale partial derivative with respect to x. You see, just to develop this, dx partial derivative of x is 1, and dy partial derivative with respect to x is 0. Attention now, this is the conic delta, okay? So this is 2x. Now, let's apply df on this basis here, the vector basis partial respect to y. You see, you just repeat df over here, this is partial respect to y. dx partial respect to y is 0, and dy times partial respect to derivative with respect to y is 1, exactly as we did over here. So this is 0 and this is 1. So this is 3y squared. Now let's add, you see, because there is a sum. You have this one plus this one, you see. So this leads to df applied to x is 3 times 2x plus 4 times 3y squared. So df at x, 6x plus 12y squared. It's quite easy now, you see. Now let's go to the right hand side. You see, this is the left hand side of 1. I called equation 2. Now let's move to the right hand side, x applied to f. You see, x applied to f. The action of a vector x on a function f is called the directional derivative, you see, by definition. So x applied to f, you just, this x is given, and f is also given. So I just substitute here and take the partial derivative. So it's quite easy. So 3 partial respect to x, x squared plus y cubed, plus 4 partial of y, x squared plus y cubed. You just compute the partial derivative, okay? So this is a 2x, and this is b, in this case 3y squared is over here. So multiply by 3, multiply by 4, I have 6x plus 12y squared. So x applied to f is 6x plus 12y squared. Now this is relation 3. Now you can compare relation 3 here with relation 2. Okay? It's equal. They are equal. So we conclude that this relation df applied to x is x applied to f, which is equation 1. Equation 1 over here. So it's quite easy if you follow exactly the definition, what we are doing. So you find this equality, okay? df applied to x is x applied to f. And f is a function. df is one form. F is 0 form. See? That's a function.